And we're back. Welcome back and happy Thursday. Today, we will continue our conversation concerning computer networks with a focus today on the network core. But before we begin, a few administrative bits. Project number 1 is due this Tuesday, the 26th of January at 11:59 and 59 seconds p.m., 1 second before midnight. Please make sure you are managing your time. Why don't we get started? So we're going to examine the network core. Now, in the network core, we're going to present the diagram that we had before. And just to jar your memory, let me select the pen. To jar your memory, we had the global ISP up above, and we had regional ISP down below. And we said the purpose of the network core is to effectively forward these units of data we call packets between the source end system or host and the destination end system or host. And we said the network core consists of what I called a switching fabric. Switching fabric. And that switching fabric consisted of a set of packet switches, these devices, and these packet switches, we said, store and forward packets from one device to the next. Now, these specific packet switches, the ones, the disks with the little X through them, those are routers. And a router is responsible for storing and forwarding packets. Now, these packets come into a router. The router examines some piece of information in that unit of data or packet, and then based on that information makes a decision as to whether or not it should forward that packet out of one link along a communication link or another. So these routers forward packets from one router to the next, so the output from one router will be the input to another. And this has a cascading effect, and eventually this packet makes its way across the internet. Each packet, when it is transmitted on a link, is transmitted at the full bandwidth capacity of that link. So let's take a look at this storing and forwarding. We said before we have a packet of size L many bits, and we said we measured the transmission rate, and we'll call that transmission rate R, and the units for the transmission rate is bits per second. That's BPS. And so in order to calculate how long it takes to send a packet, transmit it across that link, across the wire, we divide L, the size of the packet, by R, the rate. And the unit is in seconds because L is in size bits and R is in size bits or unit bits per second. If we divide L by R, L upon R, the units also divide, so that's bits divided by bits over second. In the denominator, we flip that fraction, so it becomes bits over bits times seconds. Bits cancel, and we're left with seconds. So I'm also going to talk about metric units, and metric units when we consider the size of things like bits or the rate. We're going to talk about units of 10 to the 3. So if we have 10 to the 3, which is 1,000, we use the prefix kilo. So when you see the word kilobit or kilobit, that is 10 to the 3 or 1,000 bits. If we see 10 to the 6, 10 to the 6 is 1 million. We call that a megabit. Okay? So whenever you see megabits packet, 1 megabit, that would be 1 times 10 to the 6 or 1 million bits in that packet. And it just so happens when you see little b, for example, little b BPS, that stands for bit, but when we see big B, that stands for byte, where 8 bits is equal to 1 byte. So if I said 1 kilobyte or 1K with a capital B, well, that's 1 times 10 to the 3 bytes, where a byte is 8 bits. If I said 1KB, where that's a little b, that's 1 times 10 to the 3 bits. So it's going to be really important to pay attention to the units. All right, so when we store and forward, in order for a packet to complete its forwarding across a link, this transmission, all of the bits of the packet must arrive at that destination on the other end of the communication link. So in the case of this computer here, this host, the message on the host that we want to communicate is chopped up into packets, and each packet is transmitted 1 bit at a time over the communication link. And once that last bit of the packet has been transmitted, only then is it considered successfully transmitted to whatever is on the other end of that link. And on the other end of the link in this diagram is a router or packet switch. And so for store and forward, the entire packet has to arrive at the router before it can be transmitted. And in this diagram, if we want to talk about the amount of time that it takes for a message, and specifically a packet, a unit of data, to be sent from the host on the left, we'll call that A, to the host on the right, we'll call that B, we have to make an accounting for the time it takes for that packet to be transmitted in its entirety across every single link between the source and destination. And so in this particular case, we have one link to get from host A to the router. It stores and forwards the packet across the second link to get to host B. Now, traversing one link is oftentimes called, in computer network lingo, a hop. And so this is a so-called two-hop path because we traverse the first hop or link and then the next hop or link to get from the source A to the destination B. So one of the things we talk about when we make an accounting of the total delay it takes to send a packet between two end systems across the internet is the so-called end-to-end delay. And in this particular case, because we traverse two links, we have to count or add the delay for the first link to the second link, as well as any other link we might encounter to get to the destination. Now, of course, in this case, we only have two links. So we have L many bits divided by R, the transmission rate to get across the first link, and then another L over R, many seconds, to get across the second link. If we add them together, that's equal to L over R plus L over R. That's 2 times L upon R. And so if we were to plug in some numbers, we have L is 7.5 megabits, so that's 10 to the 3 bits, and R is 1.5 megabit per second, so that's 10 to the 3 bits per second. So we divide L over R, and that delay is 7.5 over 1.5, which is 5, and the unit is seconds. So the one hop delay for a single link is L bits over R, and for L is 7.5 megabits, and R is 1.5 megabit per second. We get a total of 5-second transmission delay for a single hop. And so if we wanted the end-to-end delay, that would be 5 seconds for the first link, and another 5 seconds for the second link. All right, so when we do packet switching, the sending of packets across these packet switches, there's all sorts of other sources of delay, and there's also loss. One of the sources is that transmission delay that I alluded to in the previous slide. But whenever you get data going into a packet switch, many machines are sharing the same packet switch. More than one machine is connected to a single router. And if you have more packets, more internet or data traffic going into a router than can be transmitted at the rate for the output link going from the router, you end up having more data coming in than can leave. So what happens to that data if data arrives at a higher rate coming in than that data leaves? Well, routers also have buffer memory in the form of a queue, and this queue stores packets in the order in which they were delivered on the inbound side. And so a router or packet switch also maintains a queue. Now, of course, whenever you have a lot of packets coming in, that queue gets bigger and bigger and bigger. The line gets bigger until eventually you run out of queue space, you run out of memory. What happens then? The only alternative that a packet switch has is to drop subsequent packets. If a new packet arrives at the router and there's no space to store it, it just gets dropped. It's kind of like you go into the bank. If the line is really long, they don't let any more people into the bank after a certain point. So if the arrival rate in bits going into a link exceeds the transmission rate for packets going out of a link for a period of time, then those packets will queue. They'll wait to get transmitted out of link, and the front of queue packet is the one that gets transmitted 1 bit at a time. Packets can be dropped or incur packet loss if the buffer in the router, that queue, fills up. And so there are two core functions that these packet switches take on or perform. One is routing, and the other is forwarding. And the routing pertains to the examination of special address information within the packet that encodes the destination. And based on this destination, a forwarding decision is made. Now, this forwarding decision is the movement of the packet from the router's input to some appropriate output link. Now, associated with the bits of address information in the packet is an output link. So let's say in this schematic, a packet comes in to the router from some machine or from another router, and there's some address information that's 0111 in binary. So a table lookup is done, and that table is set, those entries are set by a routing algorithm, and for that entry 011, it says 0111, it says forward out link 2. So then the router forwards that packet out link 2, and it gets transmitted out that communication link that connects to port 2 on this particular packet switch or router. Now you notice here that all the routers have a routing algorithm running with one another. And we'll learn much more about routing, but at this juncture in the semester, we'll just say they exchange information with one another. And based on that exchanged information that the routers exchange with one another, they can figure out what the best output path is based on the address information. So core functions for these routers, which are packet switches throughout the network, but in particular, many in the network core, consists of routing and forwarding. There is an alternative to packet switching, an alternative form, of course, called circuit switching, and it goes back to the telephone system. And in circuit switching, we have the bandwidth associated with communication links is divided up into channels. And each of these channels forms a part of a so-called circuit. And whenever you want to set up a communication path between a source and a destination, part of that addressing information in the packet results in the establishment and the reservation of a channel. So here we want to send, in this diagram, a packet or signal or data from this source host, we'll call that A, to a destination host, we'll call that B. So part of the so-called call setup is the allocation of channels along these links. And so for this top link, it would allocate, for example, the second circuit here, and then maybe on this link going down, it would allocate the first circuit. Now, the difference is with this circuit switching is that once a communication path is allocated a particular circuit along the communication link, the bandwidth associated with that circuit is completely devoted to that particular communication. There's no sharing that happens. So even if, for example, host A is idle for a time, well, no one else can use that bandwidth that has been reserved for the communication path between endpoints A and B. Now, this is commonly used in traditional telephone networks, and circuit switching has its benefits as well as its drawbacks, which we'll discuss a little bit later. So some of the methods that circuit switching use, there are two major flavors. One is called frequency division multiplexing, or FDM, and the other is called time division multiplexing, or TDM. So here we have a depiction of frequency division multiplexing, FDM. We have time going along the horizontal axis, and we have frequency going along the vertical axis. And essentially what happens, if we have 4 users, we can divide our communication link up into blocks of frequencies called channels. And this is just like channels like you might have on the radio. You have maybe 105.3 WDAS FM out of Philadelphia. That is a channel of communication in the wireless radio spectrum. And so if you tune your radio to that channel, you're getting different information, that radio station, from maybe 88.7 The Bridge, which is another frequency. And so if you divide your spectrum up into blocks, each one is a quote-unquote channel, and now you can pass data down them. And so in the case of frequency division multiplexing, you're allocating channels of communication, blocks of frequencies. And every communication medium has a range of frequencies over which you can support signal information or data. And so you have each user throughout all of time is occupying one of those channels into which the communication medium's bandwidth has been divided. Let's contrast that with time division multiplexing. Time division multiplexing, again, we have time along the horizontal axis and frequency along the vertical axis. We take our channel and we have all the available spectrum, all the frequencies for the channel available at one time. But what you're going to do then is divide time up into slots. And so for some amount of time, delta t, that could be 10 milliseconds, it could be 100 milliseconds, you're going to devote a slot of time to each one of these communications. And during that period of time, only that particular user's message will have access to the spectrum or of cross-frequency range for the entire bandwidth of the communication link. And so in that case, in a round-robin fashion, we give the first user some time, the second user, third user, fourth user, back to the first, second, third, fourth, and so forth. Now, of course, with the circuit switching, in the case of FDM, if you did not use bandwidth in your channel, well, that goes unused until you release that channel back to someone else. If you are assigned a time slot, say slot number 1, and during your time slot, you don't use that bandwidth in the channel across the entire spectrum for the communication link, that just goes unused until you release it and someone else allocates it. So with circuit switching, if you're idle, no one else can use that bandwidth. Packet switching, on the other hand, does fair sharing, and it allows more users to use the network. And the reason for that is because of something called statistical sharing. Statistical sharing. And what that means is you treat each one of the hosts that want to send data on the link as a stochastic process. There's a certain probability associated with whether or not, or what percentage of the time, someone's going to be sending data. So let's give an example. Suppose you have a 1 megabit per second link, and you have a number of users. And when a user is actually sending data, and you're not sending data all the time, when it's actively sending data, you're going to send or push data into the link at a rate of 100 kilobits per second. So kilo, that's 100 times 10 to the 3 bits per second when you're active. But you're not sending, you're not active all of the time, you're only active 10% of the time. And so probabilistically, you could say the probability that a particular user is active is 0.1. And so with circuit switching example, if you have 10 users and you are allocating circuits, and let's say you have 10 channels, well, if 10 users want to use the channel, you're going to have full bandwidth usage because 10 times 100 kilo is 1 megabit. So each of these 10 users is going to use their 100 kilobit per second worth of bandwidth. Whether they're actively sending or not, it's going to be allocated. With packet switching, on the other hand, suppose you have a total of n equals 35 users. And let's suppose that the probability that a single user is active, again, it's the same number, 10%, is 0.1. And you want to know what's the probability that more than 10 users are going to be active at the same time. Well, that probability is going to be less than 0.0004. Now, if you've taken stochastic computing, this is nothing more than a binomial distribution. It's a binomial distribution where n, the number of trials, is 35. The probability of a heads, p, is equal to 0.1. And you want to know what's the probability that this binomial variable x is going to be greater than 10. Now, of course, if you've taken stochastic, you say, okay, that's 1 minus the probability that x is going to be less than equal to 10, which is just 1 minus the cumulative distribution function of this x. If you haven't taken stochastic computing, what you do is you evaluate this binomial distribution, and the binomial distribution says the probability of getting some number of heads, treating active user as a heads, is equal to n, which is 35, choose k, times p to the k, number of active, times q, which is the number, the probability of not being active, which is 0.9, to the n minus k. And so in that case, you'd evaluate this expression for n equals 35. You'd evaluate, and p is equal to 0.1, q equal to 0.9, and you take this expression for k equals 11, k equals 12, etc., all the way up to k is equal to 35, and then you'd add up all of those evaluations together. That's what this cumulative distribution function is. But nonetheless, what this says is a very small probability that you're going to have 10 users concurrently active at the same time, because you need all of these 0.1s. If you multiply 0.1 by itself 10 many times, that's a really small number. And so because it's very rare, or relatively rare, that all 10 are going to be sending at the same time, that's why you get this small number for this probability that more than 10 active users at the same time. And you get that 0.0004 because you're adding up all these factors for k equals 11, 12, etc., up to 35, given this formula, where n is equal to 35, p is equal to 0.1, q is equal to 0.9. Okay, so this is the binomial distribution, and all this is an evaluation of the binomial distribution. And the binomial answers the question, if you have a probability of getting a heads at rate p, or probability p, what's the probability if you flip it 35 times of getting more than 10 heads? Okay. So this statistical sharing means that you can have more users using the same 1 megabit link or sharing the same 1 megabit link using packet switching than if you are using circuit switching. So that's one of the benefits of packet switching. Packet switching isn't always the best solution. It depends on your application. You're going to find this a lot throughout computer networking. Several things will depend on your scenario and your situation. So packet switching is great for bursty data, data that spikes. And so it goes at a small rate and it stays around some average, and all of a sudden it shoots up and it comes back down. Packet switching is great for that. Great for bursty data. It's great for resource sharing. It's simpler. You don't have to sit there and do call setup, the allocation of these channels, whether it's frequency division or time division multiplexing. If excessive congestion is possible, i.e. you get packet delay and loss, well, you need some protocols with packet switching to get reliable transfer of data. You need something called congestion control, which we'll talk about in the transport layer segment of the semester. So one of the questions then is, with packet switching, how do you get circuit-like behavior, these bandwidth guarantees? Because it's statistical sharing, packet switching cannot give you bandwidth guarantees, because sometimes the bandwidth is being used up by someone else because they chose to, for example, watch a movie while you're trying to get work done. So bandwidth guarantees over packet switching is an all-solved problem, and if you can solve that, you'll be famous in computer networking. And so there are human analogies that you can imagine for packet switching and for circuit switching. Consider bathroom usage. You know, when you go into like a Starbucks and you ask for the key to the bathroom and it's a single person bathroom. You go inside, there's a toilet and there is a sink, and you go inside, you lock the door. That's circuit switching. You use that resource entirely for yourself, and then once you release it, someone else can use it. A rest stop bathroom where everyone goes into the same bathroom and you use up whatever stall or resources or sink that are currently available. Otherwise, you have to wait in line. That's more like packet switching. So there are analogies in the human world for the difference between packet switching and circuit switching. So the internet is structured, we said before, is a network of networks. And the end systems connect to the internet via what we called access ISPs. And these are provided by internet service providers. And there are different types of access networks: residential, university, wireless, and so forth. And the access ISPs, therefore, must be interconnected to one another so that any two hosts on different access internet service providers networks can send packets and exchange packets with one another. So this results in a network of networks, interconnected networks, which is very complex, and the evolution of these interconnected networks was driven by two forces: economics, competition in the marketplace, and policies. So the book takes a stepwise approach, and let's assume you have millions of access ISPs to which the end systems, home networks, wireless networks, enterprise networks, are connected. So how would you connect together these access networks? The naive approach, you'd imagine, is to connect each one to one another. But of course, this doesn't scale, because the complexity, big O of n squared, for the number of connections. And so if you had 1 million ISPs, that would be on order of 1 million squared many connections. That's a lot of connections. And I don't know about you, but if you were an access network, I'm sure you don't want to have 999,999 different links going out of your access network. And then what makes this even worse is if you add another one, all of a sudden, everyone else would have to have a new connection to get to that additional access network provider. So that doesn't scale. Another option, we said these global ISPs, they're much far reaching in their span for the network. They might traverse whole continents. Now, you could connect all the access ISPs to one global transit ISP. So it's a big switching fabric with a lot of routers, and the communication links span across wide distances on the geography. All right, so you could do that, okay, and that person will make all the money, And other people would say, hey, wait a minute, that's a good business. It's lucrative. I want in on the action. So if it's a viable business, there are going to be lots of competitors. One might be Sprint, one might be Level 3 Communications, another might be Cogent, another might be AT&T, for example. So then the different access network providers are going to connect to these different global ISPs. Maybe they'll maintain multiple links because they want redundancy, or maybe they might be singularly connected to a single global ISP. And so each of these global ISPs have to be interconnected then, because in order to get data from an access network connected to Level 3 communications, you need to connect to Sprint if you're on Sprint. So these global ISPs must be interconnected. And the connections between these different ISPs, they're called peering links. And that means all of the ISPs, say Sprint, will send traffic to AT&T's network, and likewise, AT&T will send traffic into Sprint's network. Now, of course, this can get quite hairy. How do they work this out? Sometimes they do it by paying money. Other times, they have an agreement where they exchange a certain amount of traffic. So if you will take, for example, 1 gigabit per second worth of data from my network, I will take 1 gigabit per second of data from your network. So they often have these so-called peering agreements about the traffic exchange between service providers. And it could be equal exchange, or it could be money. You pay me $10,000 a month to have 10 gigabit worth of data trafficking across your network into mine, for example. Or it could be a like exchange. So these facilities exist called Internet Exchange Points, where this interchange of data between global ISPs occurs. And these IXPs, Internet Exchange Points, are typically data centers, and they have router hardware from each of the global ISPs that physically have links that go to one another. Well, the global ISPs, they deal with large expanses and high bandwidth, but maybe you don't want that high of bandwidth because bandwidth costs money. And an access network might want a lower amount of bandwidth. And so the business of regional networks have popped up, and the regional serves smaller areas like the Mid-Atlantic or like the city of Philadelphia, for example. And so the regional networks are able to offer more localized service, but also a little bit more on the customer support. And so there are regional ISPs as well in this ecosystem. Now, you also have what are called content provider networks, which sort of cuts across all of this. And these are generally very large corporate concerns like Google and Microsoft, another company that does web caching called Akamai. And they deal with so much traffic, they effectively implement their own. And so they are a type of global ISP, regional ISP, and access network because they want to push content and services close to the end users. And that's how Google was able to offer Google Fiber, which was high-speed fiber optic internet to the home. They do it in various cities around the world. And so if you were to look at the structure of this network of networks, at the top we have what are called Tier 1 ISPs, those are the global providers. They're interconnected through these internet exchange points. You also have these content provider networks like Google. Then you have your regional ISPs that are closer to the network edge, to the users. And you have these access ISPs down below, and that's the interface for access that typical users, be they home users, wireless, or enterprise, might have their entry point to get their traffic onto and off of the internet. And so this is what the architecture looks like. It's hierarchical. And as you go up the hierarchy, you deal with larger amounts of bandwidth. This is a map of Sprint's network, at least for the continental United States. And here you'll see edges, long haul, between various locations. So for example, between Seattle and Chicago. For example, between Los Angeles and Seattle, between Anaheim, California, Fort Worth, Texas, and then from Fort Worth, another big hop on through, looks like the Washington, D.C. area. And so you'll also notice that some of these links go off the coast across the ocean. And those global crossings are typically implemented as undersea cables. It's much more efficient and higher bandwidth to use fiber optic communication in undersea cables underneath the seafloor or on the seafloor than to use satellite. And so if we look at these black rectangles, these are these IXPs, these peering points called points of presence. And typically we have a bunch of routers sitting in a data center, and you have routers that get data to and get data from the internet backbone, high-speed links. And then you have routers that push traffic to the particular ISPs, and then you just have an exchange of links. So here is one ISP. There's ISP A. There's another ISP, ISP B. And you notice here the links for ISP B serve all the customers, so do ISP A. And so the data for other customers through A can serve these on their own network or those on someone else's network. And they have agreements in place on the bandwidth exchange. So this is an example of undersea cabling, and this in particular is something called CCOM. And it's a series of undersea cables that serve the African continent for high-speed internet. And so this, to give you a sense of perspective, this is how big the cables are. These are adults. This is an ROV, or remotely operated underwater vehicle, and this thing lays this cabling on the sea floor, digging a trench and burying it just underneath the sea floor for stability. And this is the ship that has this cable spool, and it just drives along, guided by GPS. There's people guiding it, and it's digging a trench in the sea floor and burying these fiber optic cables. This is the cutaway and a schematic of what the undersea fiber optic cable looks like, and this is an actual cable if you were to cut it open. And so it has a very thick plastic insulator and then a series of steel cables to give it strength, because you don't want this thing stretching and being torn by different forces underneath the ground, the earth shifts and so forth. Then you have a resin insulator to keep everything nice and dry, and you have a conductor, and this conductor is there to power repeaters, because along this fiber optic strand you're sending pulses of laser light, and every so often you need to put a piece of hardware that's going to take that laser light and rebroadcast it, amplifying the strength of it. And so inside here, that's the actual set of fiber optic strands. It's not very many, they're very high speed. So this is an undersea cable, and I'm going to play this video for you a little bit to show you actual video of this ROV trenching and laying fiber optic transcontinental communication cable, internet cable, under the seafloor. So here you see the trencher, it's digging, and you see the cable behind it, and you see that roller, it's spooling it out, and then it gets dropped in the trench as the ROV scoots along. There's a trench, so it digs a trench, lays the cable inside, and then buries it with another scoop or shovel attached to the ROV. And so here's another picture of it. And then it buries it, maybe a couple feet, foot or two, whatever, underneath the seafloor. So that's an undersea cable being laid. So this is a picture of the African continent, and these lines are the CCOM lines, high-speed communication fiber optic cabling. And this went live in July 2009. They laid about 11,000 miles of cable going around the Horn of Africa. And you can see here on the east coast of Africa, west coast of Africa, Western Africa, you have lines going out to Cape Verde, and then you have off to Brazil. And then on the east coast of Africa, you have lines going off to Europe, so one to London. And if you look at some of these speeds, you have 12 terabits for the CCOM itself. CCOM is what surrounds the Horn of Africa. And then you have other 14.5 terabits going off to London from the west coast of Africa. You have 32 terabits going off to Brazil. And so you'll see that there are offshoots to the coast, and work is being done to bring that internet further inland, primarily using wireless. And so if you want to know where the future of the internet is, the future of the internet is already the African continent. Lots of venture capital, lots of very creative ventures being born in the African continent. So let's take a look at other metrics accounting for looking at the performance of internet cabling and networks. So how do loss and delay occur? Packets can accumulate in a router buffer if the arrival rate of packets coming into the link exceeds the rate at which those packets are transmitted out of the router. And when that occurs, packets will queue. They'll wait their turn to be transmitted. So here we have a packet being transmitted. It takes time to do that. And in the meantime, packets will come streaming into the router. And so you have what's called a queuing delay. And that queuing delay is the amount of time that a packet has to wait before it has its turn to be transmitted out of the link. If you have freely available buffer space, arriving packets are queued and they wait. But if that buffer fills up, you get packet loss if there are no free buffers, no space left for the arriving packets. So you can have a delay due to queuing in addition to transmission, but you can also have packet loss. So let's take a look at all of the sources of delay for a packet switch for a router. The nodal delay is the total delay for a router, and that consists of 4 components. There's the processing delay, dproc. There's the queuing delay, dq. There's a transmission delay, dtrans. And there's a propagation delay, dprop. We already talked about dprop. dq is the queuing delay, the time that a packet waits in a queue at a router before it gets its turn to be transmitted. The transmission delay is the time it takes to encode that packet as ones and zeros down this wire into signal energy for it to go down the wire. And propagation delay is the time it takes for it to physically transmit. And so the difference between transmission delay and propagation delay are very different. They're related, but they're very different from one another. It's not the same thing. And I'll be very specific about that shortly. But the processing delay, recall when I talked about how a router examines certain address information in the packet. The processing delay is the time it takes to examine that addressing information, as well as to check for errors and make the forwarding decision to look up in that routing table what link that packet should be transmitted out of. So that takes time. That's the processing delay. The queuing delay, we said, was the amount of time that the packet spends waiting for transmission. And it depends on the amount of so-called congestion. Congestion is the relative amount of packets coming into the router relative to the packets that are leaving the router. If the input data rate exceeds the output data rate, that's called congestion. And the result of congestion is that the queues start to fill up, that buffer space in the router. So let's take a look at the transmission delay. We talked about the transmission delay. That's L over R, where L is the packet's size in bits, and R is the transmission rate. Now, if we want to look at what transmission means, suppose this is our packet, and our packet consisted of 4 bits, bit 0, bit 1, bit 2, and bit 3. And so if we were going to transmit this, suppose we had 1, 0, 1, 0 as the value for bit 0, bit 1, bit 2, and bit 3. So it's 1, 0, 1, 0. So the first thing we do is we transmit the 1, okay? That gets transmitted on the wire. And let's suppose that signal was voltage at a certain frequency that's detected at the endpoint. So it takes time to transmit that. So you put that signal on the wire, and it gets detected, and it says, oh, you just sent me a 1. So then the 0 gets encoded. Maybe that's voltage at a different frequency. It goes on the wire, and then it says, oh, that's a 0. So the same thing happens for the 1 and 0. So we get that one transmitted and that one encoded as signal energy on the wire. So it says 1010. So the transmission delay is the amount of time it takes to encode each 1 and 0 bit, or each bit, as a signal energy on the wire. It takes time to do that. That's your transmission delay. But what the propagation delay is, the propagation delay says once that 1 or 0 is represented on the link, how much time does it physically take to travel down that link in order to get to the other side? That's propagation delay. And so it depends on two things. It depends on the speed of the propagation of that link, and it also depends on the length of the link. And so something like fiber optic strand is very, very fast. There's little interference. Something like satellite is relatively slow. And so transmission delay is not equal to propagation delay. They are not the same. And a lot of people, professionals even, confuse the two. Propagation and transmission are two different things. Transmission is the encoding of bits into signal energy, and the propagation is the time it takes for that signal to physically travel down the communication link, be that guided or unguided. All right. So in the book, they have an analogy based on a caravan, and you have 10 cars driving down the highway. And I don't know if you've all ever done this, but it used to be that when you have spring break, you would drive maybe from Massachusetts when I was an undergrad to Florida to stay someplace warm for spring break, and you'd have maybe 5 or 6 cars driving down the highway. And so we have such a caravan, and imagine, and this is in the book, you have 10 cars in your caravan. Now, each car is an analog for a bit. So it's like saying you have 10 bits. All right. So these cars, when they're on the highway, a length of highway is like a communication link. There's a communication link. And when these cars move down the link, that's their propagation speed. And you can imagine they propagate, and these are the numbers given in the problem in the book, at 100 kilometers per hour. So once the car is on the road, it goes 100 kilometers per hour, and the length of the link from one toll booth to the next is 100 kilometers. We also have the cars lined up in front of the toll booth, and a toll booth is like a router. It processes a bit and sends it down the roadway. It's like a transmission. Okay, so a toll booth then in the problem takes 12 seconds to service a single car, so 1 bit at a time. The question then asks, how long until the caravan is lined up in front of the second toll booth? So here's the first toll booth, here's the second toll booth. How long does it take for all 10 cars to be lined up in front of the second toll booth? In essence, it's saying how long does it take for the transmission and propagation of these 10 bits to occur. So let's think about what happens over this link. If you're going 100 kilometers per hour and you have to go 100 kilometers, well, it's going to take you 1 hour, right? Because it's 100 kilometers per hour. That's your speed. And your distance is 100 kilometers. That's 100 over 100. That's 1. And the unit is kilometers over kilometers times hour. Kilometers cancel. That's 1 hour. 1 hour is the same as 60 minutes. So we know that it takes 60 minutes for a single car to propagate down the wire. But in order to send all cars, what do you have to do? You process the first car, then you transmit. Then you process the second car, third car, up to including 10th car. So for all 10 cars to be lined up, 10 of them, in front of the second toll booth, you need to know how much time until you process that last car and it propagates to that second toll booth. So to process this 10th car, you spend 12 seconds for that car, 12 seconds for the next car, 12 seconds for each of the cars until eventually you get to that 10th car. So 10 many times we take our 12 seconds, 10 times 12, 10 cars times 12 seconds is 120 seconds, which is 2 minutes. So after 2 minutes, what happens? After 2 minutes, that 10th car, so let me draw car number 10. There's my wonderful artwork. That 10th car is on the road side of the toll booth, a window. And now it takes another hour, 60 minutes, for that 10th car to propagate. Now, at that juncture, all the other cars are either lined up in front of the toll booth or somewhere in flight in the middle. But once that 10th car makes its way to the second toll booth, you're guaranteed that all the other cars are going to be there. So it takes 2 minutes to process all that up to and including the 10th car, and then another 60 minutes to propagate. So 2 minutes plus 60 minutes is a total of 62 minutes. Okay, so let's take a look at it. The time it takes to push the entire caravan, all 10 cars, through the toll booth onto the highway is 120 seconds. This is 2 minutes. And then the time for that last car to propagate is going to be 1 hour or 60 minutes. You add 60 minutes to 2 minutes, the answer is 62 minutes. And so here, you're making an accounting for the amount of time it takes to process each car, and then you're looking at that configuration where all 10 cars are lined up, and then you add to that the amount of time it takes for the 10th car to make its way to propagate across the roadway. Okay, so here's another example. Now it uses the same numbers, but it's going to change the speed at which it propagates. You still have 100 kilometers between the first and the second toll booth. You still have 10 cars, but now it's going to propagate 10 times that, 1,000 kilometers per hour. So if you are propagating at 1,000 kilometers per hour, and you go 100 kilometers, so 100 kilometers divided by 1,000 kilometers per hour, that's equal to 1/10 kilometers over kilometers times hour. Kilometers cancel, that's 1/10 of an hour. An hour is 60 minutes, so 1/10 of 60 minutes, that's 6 minutes for the propagation speed. Instead of 60 minutes, it's 6 minutes for the propagation time to go from one toll booth to the second toll booth along the 100-kilometer roadway. Now the question then, suppose the toll booth, instead of taking 12 seconds per car, now takes 1 minute to service a car. The question that it asks is, will cars arrive to the second toll booth before all the cars are serviced at the first booth? So what it's asking is, will you have cars over here waiting at the same time you have cars line up over here? So let's think about this. So it takes 1 minute to service a car. So at 1 minute time, well, the first car is on the roadway side. And after that first car is on the roadway side, you have 9 cars out of the 10 now waiting in front of the first toll booth. Now, how long does it take that first car to propagate? We said it takes 6 minutes for any car to propagate at that 1,000 kilometers per hour. So now, after the first minute, that's 1 minute, the first car is on the roadside of the first toll booth, the roadway side. 6 minutes later, that first car is now in front of the second toll booth. Now, what happens in that 6 minutes? We just said that it takes 1 minute to service a car. So if it takes 1 minute to service a car, in the 6 minutes it takes that first car to traverse to the second toll booth, you're going to have 6 more cars. Car number 2, car number 3, car number 4, car number 5, 1, 2, 3, 4, car number 6, and car number 7 on the roadway side. Because in that 6 minutes that it takes the first car to traverse to the other side, it's going to be 6 additional cars. Now, in reality, that's not the order. The order is 2, 3, 4, 5, 6, 7. And so the moment the first car is at the second toll booth, car number 7 has just been transmitted. Car number 6 has propagated for a minute. Car number 5 has propagated for 2 minutes. 4 has propagated for 3. 3 has propagated for 4. 2 has propagated for 5 minutes, right? So what ends up happening now is if you have car 1 at the second toll booth and cars 2 through 7 that are currently on the roadway, that means car 8, car 9, and car number 10 are going to be in front of the first toll booth still. So effectively, yes, the answer is yes. After 7 minutes, the first minute to transmit the first car onto the roadway side, and then another 6 minutes for that first car to get to the second toll booth, you're going to have cars 2, 3, 4, 5, 6, and 7 on the roadway between the two toll booths, and car 8, 9, and 10 are going to be in front of the first toll booth. Okay, so again, it's important to make an accounting of both the time it takes to get transmitted and the time it takes to propagate when you answer such questions. So let's talk a little bit about queuing delay. Now, when we think about a router, well, the router pushes data out at a rate of R bits per second, and we have a packet of length L, and we have an arrival rate. Packets arrive at some amount, A packets per second. So if you have size L, the number of packets that are arriving, or the amount of data, is the size of the packets times the number of packets per second. So LA is the total amount of traffic in terms of bits that arrive or go into the router, and R is the amount of traffic in bits per second that leaves the router. And so there's one statistic called the traffic intensity, and that traffic intensity expresses the ratio between the amount of data that comes into the router, LA, and the amount of data, or the rate at which data leaves the router, R. And so if you express this ratio, LA over R, that's called the traffic intensity. It says what is the relative proportion for which information comes into the router and information leaves the router. So if LA over R is close to 0, what does that mean? It means the rate R at which data leaves the router is much greater than the amount of data that goes into the router. And if that's the case, the queues are going to be very small, and therefore your queuing delay is small, because if data leaves faster than it goes in, you don't need to store things in queues because there's nothing to build up. If LA over R is equal to 1, that means that the amount of data coming into the router is roughly equal to the amount of data leaving the router. So that means your queuing delay is going to be large because it's going to spike, but on average, LA over R is equal to 1. That means you're going to get some queuing delay, and it's going to get quite large. Now, if you have LA over R is greater than 1, that means the numerator is bigger than the denominator, which means the amount of data coming into the router is more than the amount of data leaving the router. So that means that you have far more information or work arriving than you do leaving. And what happens there is that your buffer fills up and you're going to get infinite delay, which means your packet is dropped. And so this is a depiction of traffic intensity. And LA over R, as it approaches 1, the horizontal axis is that statistic traffic intensity, that proportion. And the vertical axis is queuing delay in seconds. And so you see, as you get closer to 1, this traffic intensity, your queuing delay gets bigger and bigger and bigger. You effectively reach an asymptote consistent with 1. Because once you pierce this, you're going to have loss. And so this queuing delay is a relative relationship between the data that flows into the router and the amount of data that flows out of the router. And so real internet has delay and along the routes. And when we talk about real internet, there's a tool called traceroute that provides measurements of delay for each one of the hops along the pathway between a source and destination endpoint. And so what it does is it sends something called Internet Control Message Protocol, or ICMP packets, and we'll talk about that another time. And it sends these packets, and when it visits these packets, each router, it's called a probe, and it sets a number in these probes such that a message from the router is returned that says, hey, I got that message. All right, so the first 3 probes go out for the first hop. It starts a timer before it sends the probe and measures the amount of time that transpired when it gets a reply. And so it does those 3 and then shows you what those 3 are for the first hop, for the second hop, third hop, and so forth, going from source to destination. So this is an actual traceroute measurement. And what traceroute will give you is a bunch of information in columns. The first column is the hop. The second column is the name for that router. The third column is the IP address for that router. And then the last 3 pieces of information are those delay measurements for the first probe, second probe, and third probe. And so here what we see is a complete accounting of the delay along the path from one machine to another machine, and traceroute is the tool that allows you to do that. But not all routers are going to respond to these traceroutes, because it's deemed by some, many, and it is, that if you can identify a router, now you can exploit it. So those routers that do not participate in traceroute are going to return these stars. It says, okay, I'm here, but I'm not going to tell you who I am. And you don't get a measurement for those routers in a traceroute probe. So let's take a look at packet loss. So when you have queuing in play and you have a buffer, buffers have finite capacity, they're not infinite, you have real resources on machines. If you arrive as a packet to a full queue, you get dropped. And if you drop a packet, well, along the previous hop, it could retransmit, but most systems don't do that. And so the closer you get to the destination, the more expensive a full buffer becomes when you have loss due to congestion. So let's say you have host A, and you have one hop to a router, another hop to a router, another hop to a router, another hop to a router, to host B. Now, of course, if you have a full queue here, when you send data from host A, you pay the cost of transmission and propagation across the first link, the nodal delay and queuing delay for the router, the transmission and the propagation delay, the delay associated with this router, transmission and propagation, delay for the router, transmission and propagation. All of a sudden, boom, it's dropped. So whenever you drop a packet, the closer you get to destination, you've just wasted all of that time and effort associated with every node, every router, and every link along the way. And so when you arrive to a full queue, that packet gets dropped by the router. And certainly one strategy you could employ is to have the previous router detect that it's dropped and just resend. But that's not typically done. And so it's said that packet loss is more expensive the closer you get to the destination, because you've already spent that time and those resources to get it that far across the network. So one of the things that people are concerned about in networks is the throughput. And the throughput is the rate in bits per time at which bits are transferred between the sender and the receiver. Now you notice here, it's the experience between the sender, this might be a video streaming server, and the receiver, the machine that's viewing the video, displaying or playing in the video viewer. Now, of course, the instantaneous rate is the rate perceived between the endpoints at a given point in time, and the average rate is over longer periods of time. So here we have a server streaming a file of F many bits that it wants to send back to a client machine. You have a link capacity, a bandwidth RS, bits per second, and that's for the link between the server and your route infrastructure. And then you have link capacity for the client to get from that router infrastructure down to the client machine. And it has a link capacity, a bandwidth of R sub C, bits per second. Now, of course, you can think of data as a fluid, and a server sends its fluid or its bits into the pipe at a certain rate at which its pipe can carry that fluid. Likewise, the link to the client from the router, it's like a pipe, and it can send fluid at a rate R sub C, bits per second. Now, two things can happen. Let's imagine now that the rate of send for the server link to the router is smaller than the transmission rate for the client end. As pipes, thinking of them as fluid, would say the pipe for the server is smaller than the pipe for the client. Now, of course, it doesn't matter how big your client pipe is. The fastest rate at which you're going to see that data at the client machine is limited by this pipe at the server. And so if the server is sending at 10 megabits per second, but your pipe is 1 gigabit, you paid a lot of money for a high-speed link from Verizon, it doesn't matter how fast your bandwidth is. You're never going to get it faster than the most constrained, or the so-called bottleneck link. And that's the most constrained bandwidth link along the pathway, along the route. And the reason for that is, well, if you're transmitting at RS, the router will never see data faster than RS bits per second. So therefore, any data that comes into your link is never going to be more than a rate of RS. Your end-to-end communication between the endpoints is always limited by the slowest link's bandwidth, bottleneck link. So conversely, we could have a very big pipe for the server, RS bits per second, like let's say that's a gigabit per second, and your client machine could have a link that's 10 megabit. Now, it doesn't matter how big that server pipe is, it's only going to see at the client end-to-end for that video stream data at a rate of RC bits per second. So if you had 1 gigabit per second for that link and 10 megabit per second for the client link, you're never going to see that data faster than 10 megabit, regardless of how big that server pipe is. Again, now in this case, the client link is the bottleneck link. So this is our bottleneck link. Okay, so the link on the end-to-end path that constrains the throughput is a so-called bottleneck link. Now here I'm only showing 2 hops, but let's imagine you had 20 hops or 10 hops. That bottleneck link is going to constrain the end-to-end throughput, the rate at which the data arrives at the endpoint destination. So let's take another example, and this is more indicative of what happens on the internet. Let's say you have connection links on the server side of R sub S, and you have 10 such servers, and you have a big link here for the internet pipe of bandwidth R, and it's really, really big. It's so big, you're not really concerned about it, but it's really huge. And let's say you also have R sub C is the bandwidth of the links to the client side. Now, if you want to look at the per connection end-to-end throughput, so let's say the first server is streaming data to the first client, the second server is streaming data to the second client, and the 10th server is streaming data to the 10th client, for example. So you have 10 connections, and when you're doing statistical sharing, this packet switching is doing fair sharing of the bandwidth. So per connection, the end-to-end throughput that is perceived is going to be the minimum of the bottleneck length along the pathway. Now, because we have 10 connections, each one of these connections between server 1, client 1, server 2, client 2, up to including server 10, client 10, each one of those 10 connections is going to get an equal amount, R over 10, of that big pipe. And so you have R over 10 as the fractional bandwidth used by each of these 10 connections along this internet link, that internet infrastructure. You have R sub S is the bandwidth for each server, R sub C is the bandwidth for each client. And so the end-to-end throughput for each connection is going to be whichever of these is smaller, the RS, the RC, or the R over 10. And so in practice, the client and server-side links are often the bottleneck. But you could have a scenario if you are using a very unfortunate service provider. But usually the service providers provide so much bandwidth that this doesn't happen. The slowdown, the bottleneck, is typically at the edge, at the client side or the server side. All right, so with that, that's all I had for today. Have a great weekend. Please make sure you're working on your project. It's due on the 26th of January, which is Tuesday, and I'll see you all on Tuesday.